Let's look at some examples of principal component analysis. So suppose we have a bivariate normal distribution that has a covariance matrix given by cap sig, here a 2 by 2 matrix with entries 4, 1 in the first row, and then 1 and 4 in the second row. So this would mean that if we denote the response vector by bold X, so it contains two responses, x1 and x2, then this would be the variance of x1. The variance of x1 would be 4. The variance of x2 would be 4. And the covariance of x1 and x2 would be 1. So we're told to determine the principal component coefficient vectors for this distribution, give formulas for the principal components, and then determine the variances of the principal components. Now, we're not going to go through the mathematics of extracting characteristic roots and characteristic vectors, and I'm not going to ask you to do that ever. I will never, on an exam or daily assignment, ask you to extract characteristic roots or characteristic vectors. We're going to let the software do that for us. And so I'm just going to, for a given example, if we're asked to provide these values, I'm just going to give them to you. We could use software to do it. Some calculators will provide the characteristic roots, characteristic vectors, and so forth. So don't worry, I'm not going to have you extract these characteristic roots and characteristic vectors. Let's just know how to use them. So for this particular covariance matrix, cap sig, as on this previous slide, the characteristic roots of cap sig are lambda 1 equal to 5 and lambda 2 equal to 3. The corresponding length 1 characteristic vectors of cap sig corresponding to the two characteristic roots are C1 with entries 0.71 and 0.71, and then C2 with entries positive 0.71 and negative 0.71. So C1 is the length 1 characteristic vector of cap sig sub x corresponding to lambda 1 equal to 5, and C2 is the length 1 characteristic vector of cap sig corresponding to lambda 2 equal to 3. So these are the principal component coefficient vectors. We get the coefficients for constructing the first principal component from C1, and we get the coefficients for constructing the second principal component, y2, from C2. So again, we're denoting the original data vector by bold X. So it contains two response variables, x1 and x2. So how do we calculate the principal components y1 and y2 from x1 and x2? Well, we use these coefficient vectors to get the coefficients. So C1 had coefficients 0.71 and 0.71. And so you see here, this is the linear combination that we apply to the x vector to get y1. 0.71 times x1 plus 0.71 times x2. To get the second principal component, we use the coefficients from coefficient vector C2, and so the linear combination is 0.71 times x1 minus 0.71 times x2. And when we construct these two variables this way, y1 and y2 are uncorrelated. They have a zero covariance by construction. In fact, you might utilize the rules of covariance to verify for yourself that these two principal components are uncorrelated. Now, the principal component variances are equal to the corresponding characteristic roots. And so again, the variance of y1, which is computed in this way, the variance is lambda 1, which is equal to 5. And the variance of y2 is equal to lambda 2, the second largest principal component, which is equal to 3. So we don't have to do any calculation to determine the variances of the principal components. Those variances are given to us. They are equal to the characteristic roots of the original covariance matrix. Okay, let's look at another example. So again, we've got a bivariate response, the covariance matrix of which is this 2 by 2 matrix. So entries 4, 1 on the first row, 1 and 2 on the second row. The variance of x1 is 4. The variance of x2 is 2. The covariance of x1 and x2 is still 1. And so again, we want to answer the same questions. Determine the principal component coefficient vectors for the distribution, give formulas for the principal components, and then determine the variances of the principal components. Now it turns out that the characteristic roots of cap sig are lambda 1 equal to 4.41 and lambda 2 equal to 1.59. By the way, if you add these up, we get 6, which is the total variability associated with the original response. The length 1 characteristic vector of cap sig corresponding to lambda 1 is C1 with entries 0.92 and 0.38. The length 1 characteristic vector of cap sig corresponding to lambda 2 is C2 with entries negative 0.38 and positive 0.92. And so again, these are the vectors from which we get the coefficients for constructing the principal components from the original response. And so again, denoting the original response as bold X, containing random variables x1 and x2. The formula for calculating the first principal component for this distribution is 0.92 times x1 plus 0.38 times x2. The formula for calculating the second principal component is negative 0.38 times x1 plus positive 0.92 times x2. The variances of the principal components are 4.41 for the variance of lambda 1, variance of y1, and 1.59 for the variance of y2. Now in example 3, we've got a three-dimensional response. All right, so it's got a covariance matrix that has got 3 rows and 3 columns. All right, and so you see this covariance matrix here. And so we're again going to answer the same kinds of questions. Determine the principal component coefficient vectors for this distribution. Give formulas for the principal components, and then determine the variances of the principal components. So for this covariance matrix, the characteristic roots are lambda 1 equal to 6.73, lambda 2 equal to 3.27, and lambda 3 equal to 2.00. If you add those values up, you're going to get 12, which is the total variability associated with the original variables. The length 1 characteristic vector of cap sig corresponding to lambda 1 is C1 with entries 0.63, 0.46, and 0.63. The length 1 characteristic vector of cap sig corresponding to lambda 2 is C2 with entries negative 0.33, positive 0.89, and negative 0.33. And finally, the length 1 characteristic vector of cap sig corresponding to lambda 3 is C3 with entries positive 0.71, 0, and negative 0.71. The formula for computing the first principal component from the original 3 response variables is 0.63 times x1 plus 0.46 times x2 plus 0.63 times x3. The formula for computing the second principal component from the original variables is negative 0.33 times x1 plus positive 0.89 times x2 minus 0.33 times x3. And then finally, the formula for computing the third principal component from the original x variables is 0.71 times x1 minus 0.71 times x3. Notice that the coefficient on x2 is 0, and so in this linear combination, x2 is not participating. Now, the principal component variances, the variances of y1, y2, and y3, again are given by the characteristic roots of the original response vector. So the variance of y1 is lambda 1 equal to 6.73. The variance of y2 is lambda 2 equal to 3.27, and the variance of y3 is equal to lambda 3, which is 2.00. All right, let's look at another example. So again, we have a three-dimensional response. The covariance matrix is therefore a 3 by 3 symmetric, in this case, a positive definite matrix. All right, the characteristic roots of this covariance matrix are lambda 1 equal to 7.73, lambda 2 equal to 3.00, and lambda 3 equal to 1.63. The length 1 characteristic vector of cap sig corresponding to lambda 1 is C1. The length 1 characteristic vector of cap sig corresponding to lambda 2 is C2. And the length 1 characteristic vector of cap sig corresponding to lambda 3 is C3. And again, it's from these vectors that we get our coefficients for computing the principal components. So the formula for computing y1, the first principal component, from the original variables is 0.54 times x1 plus 0.64 times x2 plus 0.54 times x3. The second principal component is obtained from the original variables through the formula 0.71 times x1 plus 0 times x2, so x2 drops out, it's not going to participate, minus 0.71 times x3. And then finally, the third principal component, y3, is computed from the original variables through the linear combination 0.45 times x1 minus 0.77 times x2 plus 0.45 times x3. The variances of these three principal components are 7.37 for the variance of y1, 3.00 for the variance of y2, and then 1.63 for the variance of y3. Let's look at one more example. Again, a three-dimensional response. And so we've got a 3 by 3 covariance matrix. You can see here that the total variability associated with this response vector is 48, the trace of this matrix. And so we're going to answer the same kinds of questions. So the characteristic roots of cap sig are lambda 1 equal to 22.74, 14.00, and 11.26. If you add those values up, you'll get 48. The length 1 characteristic vector of cap sig corresponding to the first characteristic root is C1. The length 1 characteristic root corresponding to cap sig, the length 1 characteristic vector of cap sig corresponding to the second largest characteristic root is C2. And then the length 1 characteristic vector of cap sig corresponding to the third largest characteristic root is C3. The formula for constructing the first principal component, y1, from the original variables x1, x2, and x3 is 0.54 times x1 plus 0.64 times x2 plus 0.54 times x3. The second principal component, y2, is obtained from the original variables 0.71 times x1 plus 0 times x2 minus 0.71 times x3. And then the third principal component is calculated from the original variables via the linear combination 0.54 times x1 minus 0.77 times x2 plus 0.45 times x3. The variances of the principal components constructed in this way are the variance of x1 is 22.74. The variance of that was the variance of y1. I'm sorry. The variance of y2 is 14.00, and the variance of y3, the third principal component, is 11.26. Again, by construction, and you can verify this by using the covariance formulas. Going back, if you go back and look at the notes and the properties of covariance in our overview of distribution theory, you can use those results to investigate the covariance between y1 and y2, the covariance of y1 and y3, and the covariance of y2 and y3. And it's guaranteed, it's by construction, that these three variables are uncorrelated. They've got zero covariance. So, I think that you can see here how we use these. We're not going to be extracting, we're not going to be doing the mathematics to extract the characteristic roots and the characteristic vectors. We're going to allow the software to provide those characteristic roots and characteristic vectors for us, but we now know how to use them. Now, I would also point out that in a real-world situation where we're analyzing data using PCA, we're not actually going to construct the principal components by hand using these formulas. The software is going to have that built in. So the software in a data analysis situation is going to construct, it's going to calculate these characteristic roots. It's going to find the corresponding length 1 characteristic vectors. It's going to then construct the principal components based on those coefficient characteristic root vectors. And then it will report to us the variability associated with each of those principal components using the values for the characteristic roots that it has obtained. So it's going to do all of that work for us. All we have to do is understand where this information is coming from, what it represents, and how we can use it. Okay, so this is the end of this particular lecture video. In the next video, we're going to pick up with in the real world, the population covariance matrix is known, and so the quantities that we've just been describing, the characteristic roots and the characteristic vectors, will have to be approximated, and we'll do that approximation by using an estimated covariance matrix.